All right, this video is section 5.6 on Newton's third law. You may have noticed there wasn't a video for 5.5 because we discussed it briefly in the video for 5.3 and 5.4. 5.5 is about gravitational mass. Which happens to be equal to inertial mass. And in 5.5, we talked about the force of gravity equal to mg on Earth. Right. Since those are equivalent, we're not going to discuss that in much more detail in this course. All right, for Newton's third law, we'll want to recall that a force is an interaction, meaning that we have two things that interact, right? So say that we have an object A and an object B. And we want a force of attraction between them, let's say. And we're going to define a notation here. So this is the force due to B on A, and this is the force due to A acting on B. So our notation here, we're defining force AB as force due to A acting on B. All right, key word there is the on, right? You could just read this force A on B, right? Force of A on B. All right, so now that we've got our notation down, let's look more at what Newton's third law actually says. Newton's third law says that when two objects interact, the force of object A acting on B is equal to minus the force of object B acting on A. You may have heard this called equal and opposite, right? They're equal magnitudes. And opposite directions. All right, in more detail, they're the same type of force. So let's consider a situation. We have a table sitting on the ground, and we have a book on the table. Let's think about all the forces acting here. All right, if we look at the book, well, there's a force of gravity acting on the book. There is a normal force. As that book is compressed into the table, that normal force keeps the book from going through the table. That looks about like it on the book, right? On the table, we also have a force of gravity. And normal force, right? We could even break it up into a normal force on the left leg and a normal force on the right leg. What else do we have? We also have a normal force from the book acting on the table. So this would be F normal on the table due to the book. And this would have been on the book due to the table, if we want to set our notations. All right, is there anything else going on here? We could talk about the normal force of the table on the Earth. And we could also talk about and here I've used different colors to represent which object that they're on. So this is a force on the book. Red is a force on the table. And green is a force on the earth. So what other forces would be on the earth? Well, we would also have a force of gravity on the earth due to the book. I said it backwards. A force of gravity due to the book on the earth, and a force of gravity due to the table on the earth. All right, so I think that's all of our forces involved. So which of these are Newton's third law pairs? Well, I've kind of already given away the trick to this, is that they have to be the same type of force. But there is a common pitfall here. When you're doing a free body diagram, you're only diagramming one object in general. And you look at this diagram for the book, and the force of gravity and the normal force are the same magnitude in opposite directions. So people often want to say, well, those must be opposite equal. They must be a Newton's third law pair, but they're not, right? They're not the same type of force. A Newton's third law pair always acts on two objects, right? Because you're talking about an interaction. One force acts on one object, one force acts on the other. Your pairs here actually associated to the book would be the normal force of the book on the table. Oh, let me do my colors. The normal force of the book on the table is related to the normal force of the table on the book. Yeah. And I've gotten my labeling backwards. On the book due to the table, and on the table due to the book. Sorry. I'm trying to be consistent with the way that your book does it, and I prefer the other way. So I'll try to be consistent. Your book does on the object due to the other, right? No, it does due to on the, yeah. Right? My color coding's correctly. This is the force on the book due to the table. No. Let me double check. Let's scroll back up. I don't like this. This notation is not the one that seems natural to me. Okay, so this is B acting on A. Okay. So this should be the table acting on the book. So I've got it backwards. This is the table acting on the book. This is the book acting on the table. Sorry about that. It really is going to be hard for me to stick to that, but that is what your book uses. So I want to be consistent. Right. All right. Sorry again. So our Newton's third law pair are normal force of the table acting on the book related to the normal force of the book acting on the table. Same type of force arrives from the same interaction, equal and opposite. And the other associated to the book, we've got our force of gravity on the book due to the earth. And we've got our force of gravity, and did it again, due to the book acting on the earth, right? And this is the earth acting on the book. All right, so those would be our third law pairs associated to the book. It's interacting with the table, it's interacting with the earth. Those are the only forces acting on it. And you could see, what about the interaction between the book and the table? Right, that's this interaction. This is the interaction between the book and the earth. So each one of these acts on different objects, right? If you look at this, you'll see that it acts on two objects, right? This is the force of the table on, this is the force on the table due to the book. This is the force on the book due to the table. So they cannot appear on the same free body diagram for a single object. All right, I'm using free body diagram a lot, and if you're just looking through the chapter notes, we haven't really talked about that yet. We've talked about that in class extensively, though. So let's use this point to talk about free body diagrams, because I believe this is where your book introduces it also. So a free body diagram uses a point approximation for the object, and it graphs each force acting on it. So let's look at the book. The book has a normal force from the table, and it has the force of gravity, and that's it. In this case, it's one-dimensional, so I might say the plus y direction. And at the end of the last video, I said that we're going to use these free body diagrams to make our equations of motion using Newton's second law. So if we now apply Newton's second law, I've chosen my coordinate system. So, and this is a vector equation. So now I can say sum of forces in the y direction is equal to ma in the y direction. Sum of forces in the x direction is equal to ma in the x direction. There are no forces in the x direction, so I'm not interested in it for this situation. It's a one-dimensional case. So since I chose up as my positive direction, I'm going to say positive, the normal force. Well, the force of gravity is down, so I'm going to do negative here. And you'll note that by inserting these signs for the direction, these are just magnitudes now. That's something to keep in mind, but we don't usually explicitly say it, right? What we'll usually say is we'll just write Fn minus Fg equals Ma. And it's understood that once you've input your direction, that these are just magnitudes. What that means is they should all be positive definite values, right? You shouldn't get a negative value out unless you assumed the wrong direction. That's okay. If you assume the wrong direction on your diagram, then at the end, you just have to say, oh, okay, my sign was wrong, so it's actually in the other direction. And that's fine. But you should be aware that these are magnitudes the way that we have them set up. All right, so let's look at a more complicated one. Let's look at an object on a ramp. And this is a case to introduce the idea of direction, right? If I just am given this object on a ramp, well, I know I've got a force of gravity. I know I've got a normal force. And if it's not accelerating, then there has to be some other force. Let's just for now say that there's no friction, since we haven't really introduced friction yet. So here's kind of my physical sketch. So let's do a free body diagram now. If this does accelerate, as it looks like it would because there's no friction, it's going to accelerate down the ramp. Remember, my rule of thumb is one of your coordinate axes needs to be in the direction of the acceleration. I'm going to use my x direction down the axis and my y direction perpendicular to the x direction. So sketch in my axis on my free body diagram. We've got our positive x direction and we've got our positive y direction. All right, so our normal force is on our coordinate axis, so that's fine. If we now want to break up into components, I've got my normal force and I've got my force of gravity. My normal force is not in the x direction, it's in the positive y direction. But I have components for my force of gravity, so I need to figure that out. For a typical incline problem, you'll know what the angle of the ramp is. So we need to figure out how to relate that angle of the ramp to one of these angles so that we can figure out what our components are for gravity. So there are a couple of ways to do this. So if I call this angle theta, I can think of this as being rotated from being vertical. So let's start with, horizontal. Let's start with a standard coordinate axis. And we're now going to rotate that axis to my primed coordinate axis here. All right, so if this rotated theta degrees, the axis rotates theta degrees too. So now if I look at a vertical line here, like gravity, right? For now, I'm just going to stick it as a general vertical line. Then this angle is the same rotation as this. So this angle is theta. All right, that's easier to see if you actually take a physical object and rotate it maybe. But, oh, it's not lining up. But we can also do it with some more straightforward geometry. Let's look at the straightforward geometry as well. So if we just look at some geometry, here's my box on a ramp. Here's my angle theta. Here's my force of gravity that's vertical. Okay. Now I can say, well, this is my horizontal because I'm measuring the incline of the ramp from horizontal, and this is vertical, so that makes this a right angle, which means that this angle phi is equal to 90 minus theta, right? Because 180 degrees in a triangle. So if I now look at my tilted coordinate axis, which is parallel and perpendicular to the surface here, so these are all right angles too. What I look at there, well, now I've got this right angle. Let me scoot this over. It'll make it a little clearer. There. Now I've got this right angle, and I've got this angle phi. So that's 90 minus phi. Well, 90 minus phi is the same thing as 90 minus theta, right? Because I can add theta to both sides and subtract phi. Right? That's an equivalent equation there. So I can now say, oh no, I erased it. There's my block. There's my force of gravity. There's my coordinate axis and my right angle. All right. So I can rearrange my equation, and this is still true. And I can take this right angle minus phi and get theta. So that again shows that the angle between our gravity and our primed coordinate axis is the same as the angle of incline. So we can go up here and say, right here, the angle between gravity and our prime coordinate axis is the angle of incline. All right, so now we need to do trig associated to that. If we want to do our trig associated to that, well, here's my gravity. Let me draw in my prime coordinate axis. It's really hard to hit your target sometimes with the sketch pad. All right, so remember we said that your components always have to be perpendicular to your axes. So my x component of gravity is going to look like this. And my y component of gravity is going to look like this. Putting me a right angle right here so that my hypotenuse is the total vector. This is another of those pitfalls. I've seen a lot of people want to draw a right angle right here next to the force of gravity, but then your hypotenuse is on the y-axis and it's not the correct components, right? So that's a pitfall to avoid. Remember that your components always have to be parallel to your axes. And in this case, we don't have a horizontal axis, we have this rotated axis. And this, oh, I did it again. The pen's so sensitive to clicking back and forth. In this case, we know the angle of inclines here. So this gives us a triangle we can now deal with. And we note that the y component is actually adjacent. And the x component is our opposite. So our trig is not those ones that we had drilled into us in trig, right? In this case, FGX is going to be FG sine theta, and FGY is going to be FG cosine theta. That's not F times G, that's F sub G. All right, so now we could go back to our chart up here. This would be FG sine theta, FG cosine theta. And then we could use that to form our equations of motion. In this case, in our x direction, we only have one force. In our y direction, these have two forces. And this is one trick some people do in their table here. Add up all your forces and it's equal to MA, right? So this double line here represents all your force components, and then your summation components where you have M times A. Again, we'll do a lot of free body diagram and force equation practice, but this is the section in the book that introduces it.